All right, so in this lesson, we're going to focus on understanding the continuity of limits, and we're going to look at one-sided limits. And then we're also going to do some practice and, and we're obviously going to learn about what's called the intermediate value theorem. This is actually a big thing that you're tested on if you're in AP calculus. So it's important that you understand this and practice it, especially if you want to do well going into your AP, exam. Anyways, so starting off, we're going to talk about what it means for a function to be continuous, and it's pretty much the same meaning as you would think in everyday life. Like it's just like that the graph of the function, doesn't, like stop, or it doesn't have like any holes, doesn't have any jumps. One way to remember is like the pencil rule. If you can draw the graph without having to pick up your pencil or pen, then the graph is continuous. Now, when a graph is discontinuous, or when it does have, a hole or jump or gas, we say it's, discontinuous at some point. Now, there's different ways this can apply. So, there's two general categories that we distinguish that we distinguish discontinuities. We say they're either removable or non-removable. So the way we define a removable versus the non-removable discontinuity is we say it's removable if you can make the function continuous by defining or redefining the function at C, or f at C. And this is actually spelled wrong, redefining. Doesn't look right. Okay. So let's look at a couple of different examples of how discontinuity can occur on a graph. So here we have three different graphs, broken up in different ways. And here we have holes. We have holes. We have a hole here, here, and here on the interval A, B with C in the middle. Now, there's a discontinuity at C. So essentially, this point is, if it was filled, it would be C, it would be f of C, but f of C is not defined. So we say that f of C is not defined and we say there's a removable discontinuity at C. And there is a removable discontinuity at C. Discontinuity at C. Let me try to divide this up so we don't interfere with the graphs. Okay. No, my day. Okay, so why do we say it's removable? Well, because we simply can just name a point, a point at f at C, C f of C, whatever this. Let's say that this point was let's say if it was like at 3, 3. If we just define the point 3, 3, so we say f of 3 is 3, then it would be back there and the function would be continuous. So since we can just redefine it easily, so the graph is continuous, we say it's removable. Now this guy, it's again on an open interval, f of C is actually defined, but we jump from here. We jump from here to here. So as we're approaching C, from the left, we're going to this value, but when we're approaching C from the right, we're going to this value. So we kind of have what's called, I tend to call this like a jump. We have like a jump discontinuity. Think about it just as you would normally think what a jump is. You're jumping, you're jumping from one point to another, like if you're falling off a cliff. So since the graph doesn't approach the same value from the left and right at C, we say it's the limit as x approaches C of f of x. It does not exist. And there's a non-removable discontinuity. A non-removable discontinuity at C. Now, why do we say it's non-removable? Because we can't just redefine f of c to make the graph continuous at c. And first off, f of c is already defined. F of c is you define, whatever this point is. Let's actually label it to make it clear. This is c f of c. So changing that point to be this one wouldn't connect the graph. And you can't, to make the connected graph, you couldn't make like another, you kind of make a vertical line because then they want to be a function of x. So there's no simple way to where you can just redefine f of c to connect the graph and to make it continuous. So that's why we say it's a non-removable discontinuity. Okay, now the last one, here we got a graph that has a hole at c, but then there's a point here defined. So this point is defined c f of c. So the graph is discontinuous. We have a hole. We have a hole in the graph where you can say, a gap. I like to say hole. It's easier for me to remember because it reminds me of a circle, an open circle. So it's discontinuous. This is discontinuous. It's a discontinuous graph, and so we say at the limit, if I can get my pencil to work, the limit as x approaches c of f of x is not equal to f of c. But however, if we just redefine f of c to be this value, let's say this value was, 3, then the graph would be continuous. It would be easily fixed. It would connect. So we can say that there's a removable discontinuity of c. Discontinuity at c. Okay, so let's continue with some more concepts of what it means for a function to be continuous. So let's look at a formal definition of the continuity. So for a function to be continuous at a point c, it has to have these three conditions met. F of c has to be defined. The limit as x approaches c of f of x needs to exist, and this limit also has to be equal to f of c. So if those three are met, then we can say that that's the minimum. We can say that well, actually no. I mean, I can't actually really think of any cases where if this is met, at least in the math of the real numbers so that we've learned so far. This will be all right. So when you want to show that a function is continuous algebraically, let's say, show these conditions are met, then you'll be good. Now when we're dealing with an open interval, we say that the function is continuous if it's continuous at each point in the interval, and we say that a function is continuous everywhere if it's defined on the entire real number line, from negative infinity to infinity. So we say every common phrase, everywhere continuous. Makes sense. You've probably heard it before. So let's go through a couple of examples now of what we would discuss when we were looking at the continuity of different types of functions. So the first one we have, the f of x is equal to 1 over x. So let's just draw a sketch of what this would look like. You should know what this looks like off the top of your head. And it's going to look like this pretty cool, like parabola. Now, this graph or this function is not defined for values, along the x-axis. So for the values y equals 0, and the value and the line, or the line y equals 0 and the line x equals 0. So those are, we know, as we learned before in pre-cal, we have two asymptotes. We have vertical and horizontal asymptote. So we have discontinuities. So if we're looking at this function of x, discontinuities for x equals 0. And since this graph, goes towards infinity on this end, and it's approaching infinity over here. But when you're on this side, it approaches negative infinity as you go towards 0. There's no simple way to fix that discontinuity. So we say that there's a non-removable discontinuity at x equals 0. All right, I'm still fixing some glare on my screen. Hopefully it looks good now. Anyways, now let's look at the next one. Let's look at B. So that was A. Bubble that. So for B, we have g of x is equal to x squared minus 1 over x minus 1. So let's break this down a little bit. What we can do is factor. Actually, let me do this graph down here. This will be a little easier to work with. So if we have g of x is equal to, x squared minus 1, but we can factor that into x minus 1 times x plus 1. And that'll be over still x minus 1. And so what you can do is cancel those x minus 1 groups, and you'll just get x plus 1. So if you remember from the previous lesson, this graph is essentially the same as the graph of x plus 1, except that there's going to be a hole for x equals 1, because when you plug x equals 1 into this function, you're going to get undefined value because you're going to have 0 in the denominator. So let me draw a sketch of this over here. Kind of regret putting this graph down here now. It's actually smaller than I thought, but anyways. The x plus 1 graph we know is just a, our basic, linear equation. Negative, negative 1, 0 are the intercepts, and 0, 1. But again, when you plug x equals 1 into this graph of x plus 1, it would normally be, actually, let me erase that. Normally, it would normally be, at 2. But since this graph is undefined for x equals 1, we're going to have a hole at the point 1, 2. We have a hole at the point 1, 2, but this can be easily changed if we just define f of 1 to be 2. So we have we have a removable discontinuity at x for x equals 1, or at x equals 1, you could say. Now, when you have the graph of these, it seems to be like a little more intuitive to understand when you have a removable or non-removable discontinuity, because when you have a hole, it's kind of just like you kind of just fill it back in, as long as again the graph is just only has that hole. The limit exists at that point. All right, now let's look at C now. So here we have h of x equals x plus 1 when x is less than or equal to 0, and it's equal to x squared plus 1 when x is more than 0. So we have a piecewise function. So let's look at what this would look like. Let's see what this would look like. It's not too hard if you just think about it for a second. And let me actually draw the graph a little more over here. Should organize this differently, but anyways. All right, so what we have to the right is that parabola, and to the left of 0, we have a linear equation. So we have a straight line equation. Now, when we plug 0 in, we're going to use this function. So then we're going to have a point at 0, 1. So let me actually use my other pen here, 0, 1. The graph will be at 0, 1. Now to the left, it's going to, just follow this. It'll be a straight line, a slope of 1. So we'll be doing this sort of thing. So I'll have a point, it'll go through -1, 0. I don't know why I made this line so thick. So linear on that side. Now to the right, we have x squared plus 1 as our equation. And this, actually just is a parabola with this vertex at 0, 1. So it just, goes like this. If you plug x equals 1 into here, you would have, it would go through the point, 1, 2, and veer off just like that. So even though this graph has two different equations to the right and left of x equals 0, since the graph approaches and in this case actually equals the same value at x equals 0, there's no discontinuities, there's no hole, there's no non-removable, and none of that you have to worry about. We just say that the graph is continuous everywhere, because you can plug any value into here and any value into here, and there's no holes, gaps, or anything. So it's continuous on the entire real number line. Okay, you can say continuous everywhere, or everywhere continuous. Let's go ahead, let's write that. Everywhere. I don't know what that is. Everywhere continuous. All right, last one. Y equals the sine of x. You all should definitely know what that looks like. So, everyday trig that we're so used to. Just a graph that, that goes like that. Let me see if I can do my best. It does this repeating pattern. Y equals the sine of x. I don't know what's going on with my pencil. But now, this graph, doesn't ever get larger than 1, doesn't ever get smaller than -1. But, there's no hole, there's no gap. It just oscillates back and forth. and it's not undefined for anywhere, so it's just, again, continuous everywhere, or everywhere continuous, we can say. And let me go ahead and write. Okay, so let's look a little further into like how limits can work, and we're now going to talk about what are known as one-sided limits. So as we've as you kind of been understanding that a graph can approach a point differently from the one side and it can from the other side, and we basically say it's left side, right side, or negative side, positive side. So for example, here we have this function f of x, and this is show that x is approaching c from the left side, and here's our here's our value L, so we can say that this is c comma f of c, and we can see f of c is equal to L. So how do we say this? Well, what we say is that the limit of f of x as x approaches c from the positive side is equal to L. So let's write this actually formally. The limit as x approaches c, and what we do is we use this little symbol, or the positive symbol, right with our subscript, and this lets us know this is approaching from the positive side of the right side of f of x is equal to L. We also call this, let's say, the right-hand limit. Because we're approaching from the right side. So positive side, right side limit, same deal. Now let's look at the other side. Well, if we're coming from the left side, so we're approaching c from the negative side. They're going in this direction, and we're still getting to that point, c f of c. So what we say is that the limit as x approaches c from the negative side, and we use a negative symbol in place of the positive symbol of f of x is equal to L. And likewise, we also call this like the left-hand limit. So and this helps us further define functions that don't have the general limit defined. Because if we can at least describe how one side of function behaves as it's approaching a number, it'll give us some insight of the function instead of just saying the limit doesn't exist and stopping there. So let's see how we would apply this if we're going to describe the limit of this function here, where f of x is equal to the square root of 4 minus x squared, as we approach -2 from the right. Well, first let's recall what this even is, and if you remember your pre-cal, this is just a semicircle. Semicircle with I don't know what's up with my writing today. Writing very strange. Anyways. So semicircle with a radius of 2. Something like that. Something like that. So we have a point here, -2, 0, and a point here is 2, 0. So this is I actually use my pink. This is my function f of x. So what are we talking about when we have this? Well, we're talking about as we approach this number from this side. So we're coming along this path. This will be the right-hand limit or the the limit from the positive side of the function. So as it's approaching -2 from the positive side, the graph is going to eventually equal 0. So we say the limit I don't know what's up with my pencils. I apologize if this is confusing. The limit as x approaches -2 from the right side, so from the positive side of f of x is equal to 0. That value there is 0. That's simple. Because remember, like, this is an example where, the graph doesn't exist. There's no graph to the left of -2. So when we just say what's the limit at -2, we're kind of like, well, the graph stops at -2. It doesn't go any further to the left. So you can't really answer that per se. But when you say when we specify the one-sided limit, in this case from the right side, we can actually answer the question and be properly, I guess, correct. All right, now let's look at what's called a step function, or we also call it, well, it's formally greatest integer function. We call it a step function because it looks like steps. So this is something you may not ever really see unless you go into engineering or sciences or something, because it's just the notation's kind of different, so it throws students off. And if you just don't know notation, you just won't know the graph. There's no way to know what this is, so unless you've seen it before. So what this is well, let me actually write it. So it's basically a piecewise graph. It's a piecewise graph with horizontal line segments, but they're defined at one point and not the other, depending on what graph you're talking about. Because we actually have the lowest integer function that goes the other way. I'll look at that. We'll look at that later. But in this case, what's going on here is that we have a graph defined at 0 and going all the way to the right here, and it has an open circle at 1, or at 1. So we have again this point at 1, 0, and the origin at 0, 0. So it has a hole at 1, 0, but it's still defined for x equals 1 because you have then the next step looking like this. The next step at 1, 1 defined, but then at 1 or at 2, 1, it's not defined. But going up further, you have 2, 2, 2 defined, but not 3, 2. And so on and so forth. Now, if we went to the left side, it would be the same sort of thing. You would have an open circle at 0, -1, and a closed circle you would have at -1, -1. And below that, open circle at -1, -2, and a closed circle at -2, -2. So that's why we also call it a step function, but the greatest integer function, because the value stays as the greatest it can along each part, along each subinterval for x is 0, x is 1, x is 2, and so forth. Or I'm sorry, I mean like y is 0, y is 1, y is 2. So what's going on here? So we want to find the limit as x approaches 0 from the left and right. So as x is approaching 0 from the left, we're gonna be on this part of the graph. We're gonna be going towards this side. So we say the limit as x approaches 0 from the negative side is going to be that point right there. Which is going to be -1. Well, if we're approaching 0 from the positive side, we're going to be on this step right here. So the limit as x approaches 0 from the positive side will actually just be 0. When x approaches 0 from the positive side of x is x equals 0.